Hello, and welcome to the second lesson on gravitational fields. Today's lesson is all about field lines. Field lines are ways in which we show how a force is acting on things. It's a very basic concept, but actually an incredibly useful one, because it allows us to see how different forces are acting within their fields. We use the same concept of field lines for all the different fields. So today we're going to be concentrating on gravitational fields, but what we learn today and over the next few lessons we can actually apply to all the other fields that we learn about: electrostatic fields, magnetic fields, etc., etc. You could even draw them for the strong nuclear force if you wanted to. What I'm going to do now is I'm actually going to show you some field lines, because even though they're just a thing we make up, it turns out there's a way in which we can sort of see something a bit like them. The way that works is like this. So what we have here are some iron filings suspended in oil, and they can sort of freely move around. However, if I put them over a magnet and give them a little shake like this, what you'll start to see happen quite neatly are curved lines start to form in the iron filings. You see here quite clearly this lovely curve here moving around, and they get wider and wider as they move further away from the magnet. Those are actually analogous to field lines, and it's interesting they show up in the filings. So we can see that field lines are going to be sort of often a bit curved and pointing towards things. That actually gives a few hints to how they actually work. So, how do field lines work? Well, here we have a drawing of some field lines. And what we have here is we've got a planet, let's say the Earth or whatever, and the field lines are pointing towards it. So why is that? Well, to see that, we've got the rules of the field lines. The first and most important rule of a gravitational field line is it shows you the force on a test mass. So the field line at any point shows you the force that would happen if you got a test mass. That just means a mass small enough that it isn't going to show up in your field line, so an infinitesimally small mass. If you were to put it at that point, what would be the force on it at that point? Now you should know that forces are a vector, so that's why all these lines have an arrow. So if we were at this point here, it's a little test mass there, we pull towards the Earth, that's why the arrow points towards the Earth. If you're here, we pull that way, here you pull that way, etc., etc. So that is what they show. Fundamentally, if anyone ever asks you what a field line is, it's the force on a test blank. Gravitational field will be a test mass, electrostatic field will be a test charge, etc., etc. So that is the most important rule of a field line. It's the force acting on a test, whatever it is, gravitational field lines test mass, and it needs an arrow because forces are a vector. So it's not just enough to have magnitude, you also need direction. The next thing is they never touch. If you ever drawn a diagram and your field lines are touching, you messed up. Which would make sense, because at any given point the force on it has to be in a given direction, which would tell us that this is not just the force, but the resultant force, the overall force. Imagine there are two planets, you're either going to be pulled towards one or pulled towards the other. The overall force can't be pulling you forwards and backwards. That's not how forces work. There's always a resultant force. We should know that. So therefore they can never touch, because the overall force on a mass has to be just in a single direction. And then finally, how close the lines are together tells us how strong the field is. More field lines clumped up together will mean the field is stronger at that point. So that's how we get across the magnitude part of the vector. So the direction is the arrow, the magnitude is how many lines are close together. Now, this is just a planet, so the lines should be roughly equally spaced all the way around, because it doesn't matter where you are around a spherical planet, you'll be pulled with similar force all the way around. But sometimes we might have, a really heavy thing over here, in which case you'd have more field lines near the heavy thing. fewer field lines near a lighter thing, so on and so forth. The questions I want you to do before you watch the second video are all drawing your own field lines in different situations. And I want you to actually get a pen and paper. Don't just think about it. Actually draw them and puzzle them out. It'll take you slightly longer than you think it will, but it'll be worth it, because then you'll be using your brain. You won't just be passively watching me. So when you've done that, and you've answered the questions, go and watch the second video, and I'll show you how it's done.